today we are going to learn about booth multiplier. Last time we saw sequential multiplier, so this is a slightly better version of a binary multiplier. Okay, so before taking on booth algorithm, to understand that, let's just see how multiplication is done in a binary number. So we'll take this example of 3 into 14. Okay, so 3 in binary stands for 0 0 1 1, and right, 14 stands for 1 1 1 0. So if you multiply it, now I am doing some modifications. Instead of representing 14 as a binary number like this, I am going to represent it as 2 to the power of 4 minus 2 to the power of 1. Okay, why I am doing this, and I'll tell you later on, right? So I am going to write 2 to the power of 4 minus 2 to the power of 1, right? And then I am going to open this bracket. So I am writing into 2 to the power of 4 and into 2 to the power of minus 2 to the power of 1. So again, you multiply these two, you will get the same result, right? So so what is the advantage of writing like this? We will see that. Okay, so let me go to the next slide. Okay, now I am taking one more example out here, right? So 3 into 51. So this is 51, right? So in the previous case, why did I write 2 to the power of 4 and 2 to the power of 1? Okay, let me explain it here. Okay, so 51 is represented like this, right? So this is the sixth digit, right? It is 1 2 3 4 5 6. Okay, 0, I am not starting from 0, mind you, I am starting it from 1 here, right? So there is 0 also here. So generally you call this 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, like this. But I am assuming there is 2 to the power of 0 is again 1, which is available here in the left. So from here 2 to the power of 1, 2 to the power of 2, 3, 4, 5, 6, right? So this is 2 to the power of 6. Again here 2 to the power of 4 is there are two ones, and then there is a 0 here. So I am writing minus 2 to the power of 4 here. Again there are two zeros left here, then I am writing this as 2 to the power of 2, and this again 2 to the power of minus 1. Okay, so wherever there are ones, when there is a starting of a 1, I am writing plus, and when there is an ending of a 1, I am writing minus. Okay, similarly a starting of a 1 I am writing plus, and ending of a 1 I am writing minus. Okay, so is this aspect clear, and why and how it is written here? This, anybody has got a doubt? No? Okay, so it will appear little vague here. So we will see how this is done. So what what we are doing is, see, whenever you are multiplying a number, right? So this number is being split into small binary bits, right, into just small binary bits. So whenever there are ones, whenever there is a 1 which is starting in the sequence, okay, you start adding it, and whenever there is a transition from 1 to 0, you subtract it. Again you take the sequence like this. Whenever there is a 0 to 1 sequence, you add it, and when there is a sequence from 1 to 0, you subtract it. Okay, here we are assuming there is one more 2 to the power of 0 here it is there. Okay, and also when we are moving from 1 to 1, we are not doing anything. So 2 to the power of 5 is not available. Similarly from 0 to 0, you don't do anything. 0 to 1, okay, you add 2 to the power of 2, and 1 to 1 you add 2 to the power of 1 to 1 you don't do anything, and the last bit is a 0 here. So 1 to 0, we'll put a 0 here, in the algorithm we'll put a 0 here. So 1 to 0 will make it 2 to the power of minus 1. Okay, so this is the normal multiplication. If you try to do this in this case also, if you see, you are doing the first one, it is a 1, so you have put 2 to the power of 4. Then 1 to 1 we are not doing anything, 1 to 1 we are not doing anything. Then 1 to 0, okay, there is a transition, so you are putting a minus there, right? So this is the kind of algorithm. It takes the one of the bits, and it keeps moving from the left to right. Okay, so you keep seeing from left to right, or you can move from back to from this side also from. So whenever there is an 0 to 1 transition, right, you add, and there is a 1 to 0 transition, you subtract. Okay, so this is the algorithm basically, it works. So this is the Booth's algorithm, works exactly on this philosophy. So you have an start, you have a equal to 0 initially, right, you take a equal to 0, this is an a, this is an accumulator. Okay, in the accumulator you feed a equal to 0, right, and on then there is another the q, which is to be multiplier, you load that out here, right, this is this bit. Okay, this is this bit, you put that bit there, and then you take one more additional q minus 1. Okay, you take q minus 1, which is one more bit data, you take it here, you are going to put it into one more register. N is the number of counts. So we'll keep shift, like last time we learnt, we are going to shift it 4 times. So similarly here also we are going to shift it in 4 times, like what did in the last class. It is just the extension of the sequential multiplier which we did last time. So here also we are going to shift and do the operations. Okay, the only difference which comes here is, okay, here we have, okay, q this q, last time we were monitoring this last bit, now here we have put one more storage bit here, right, and we are going to monitor these two together, right, and we are going to take a decision whether to add or to subtract. Last time we did only addition, here we will do a subtraction also, right. So if you see here, now I have written it like here. So it is best understood by an example. So here m is 0001. Okay, what does 0101 stands for? It stands for 5, right. Q stands for 6, right. So this stands for 6. So this number is written, q is written here now here. Okay, accumulator is 0000. Initially the accumulator is 0 out here. Qn minus 1, Qn minus 1. Okay, let me, before the algorithm, let me show you. Okay, let's do this only, and then we'll go to that. Okay, so this is q is equal to 0, n equal to 4. Now if it is 00, if it is 00, I am not going to do any changes in the accumulator. So accumulator remains 000 here. Okay, q come and then q is this, right, here and no change in accumulator. This you are going to shift it right in the next step. Okay, it is going to be shifted. There is no change in the accumulator 000. So if I am going to shift it right to 0000, now I am doing an arithmetic shift. Okay, understand, this is an arithmetic shift. In the last thing we always pushed a 0 when we are shifting here, but in this case we are going to, whatever is the last bit, the same bit will get pushed. Okay, in the example it will be clear. So it is 0000 here, and q is 0011. So we have shifted here, so this 0 has come. In the next cycle, if you see, it is 1 and 0 here, right, it is 1 and 0. If it is 1 and 0, that means it has to be this a has to be replaced by a minus m, right. How do we a minus 1? M is stored here, right. So minus m is 1011. So last time we were adding a and m, here we are going to subtract a and m. Okay, because it is 10. Last time it was only 0. If it were 0, this a was getting as such replicated below. Here it is 10. 10 means you got to subtract a m from a, right. So you take m's complement and add it. So you write m's complement here, right. So you have q here, you have 0 here, right. So this is the state. Now in the, what about in the, and then after, once you have done that, again you shift it. Now while shifting, instead of 0 pushing in a 0 here, we'll be pushing in a 1 here from the right hand side, because this is already a 1. So this becomes 1101, right. So this becomes, so this is shifted here, this is shifted here. In the next cycle you have 1 1 available here. So 1 1 means it remains same. So accumulator is going to remain the same here, and then you are going to push it towards the right. So you continue that till you get the final answer. I'll take on a better example. I have drawn it in an Excel sheet, so that will be clear. So if you understand this algorithm, what we are going to do is we are going to put the initial accumulator to 0, q minus 1. This is an additional register. This is also we are going to put it to 0, right? And then we are going to compare q0 and q1. If both are 1 or both are 0, you just shift it, arithmetic shift. Remember, this is arithmetic. You are going to shift it to right. If it is 0 1, then you add a plus m. If it is 1 0, you do a equal to a minus m. Okay, and then you have a counter, so it will keep repeating these things. So in an hardware, how it is implemented is shown here, right? You have m, you have an add or subtract button, and then you have then accumulator a, then you have q, you have q minus 1. So into the q also we initially load the data, right? So you are going to compare q and q1 both. So if you see this, both one input data is going to a controller. So this controller will give a command either to add or subtract based on the data q1, which we saw here. 0 0 and 1 1 do nothing, and for 0 1 add and 1 0 subtract. So that command will be add or subtract will be given here, right? And then there is a counter, which is number of bits. Okay, if you are doing a 4-bit operation, after 4-bit operation, this counter would stop, or if it so this is the counter which will give to the controller. Okay, so I am sure it is still not very clear, but we'll take on one example. So after this example, if you have any doubt, then we will speak about that. So initially I am going to multiply 5 into 6, right? So it is a, this is q. So initially I am going to put accumulator 0, okay, and a is 0 1 0 1. I have put this number in. This is the m. Okay, this is the m, and this is q, right? So it is q is 0 0 1 0, which is equivalent to 6, right? So now I am initially, this is the condition, right? I have put 0 0 here, I have put 0 1 0 0 here, and this is initializing to 0, n is equal to 0. Is the first line clear to all of you? We'll go line by line. If you understand this table, then we will revisit the block diagram and circuit diagram. It will be clear. Okay, is this first line clear to all of you? We are doing 5 into 6. In accumulator we have put 0. Okay, 5 is in the m register, right? And this is q, right? So now if you see, I am going to compare 0 and 0. Okay, if it is 0 and 0, I don't have to do anything, right? So accumulator will remain 0 0 0 0 here, q will remain 0 0 as such, and a q will also. And then I am going to shift it right. Okay, since I am going to shift it right, arithmetic right, remember this is an arithmetic right. So I will push one more 0 from this side. So 0 has come in, and 1 0 comes into the q. Okay, these are connected in series, right? It has come to q, and this 0 which was there has got pushed out here. Okay, so this is first cycle is over. In the second cycle, it is 1 0. 1 0 means in the next step, okay, whenever the second clock comes, it has to subtract, okay, because it is 1 0 here. 1 0 means if it has to subtract a from m, right? So instead of subtracting this, you will add the complement, right? So this should be m. In fact, it should not be a. Yeah, it is a. So it is 1 0 1 1. It should be m. Sorry, this should be m. So complement is 1 0 1 1, right? So if you do the subtraction, that is 0 plus this, okay, minus m. This is minus m. Okay, so you are getting 1 0 1 1, right? So this is going to remain same here, this is going to remain here. Again shift right, so you are going to push it again here. Now see the difference here. Last time we had pushed a 0 here, this is arithmetic right. So you have an 1 which is coming in from here now. Okay, whatever is the last digit, that gets coming in from the left hand side. Okay, shift right, from the left hand side, this is 1 here. So this is the most important thing which you have to remember in the Booth algorithm. This has to be 1 here. So 1 comes in here, right? So now if you see, okay, now it is 1 1 1 1 means you do nothing. So this same thing goes nothing, it comes down here as it is, and this comes as it is, this comes in the third clock. If you see, then it is 1 1, so you have done nothing. Okay, after having done that, you again shift it right, so again one more 1 comes in, so this is 0 here, this one comes here, so it has become 2 ones here, 0. Now 0 1 0 1 indicates it has to add in the next clock cycle. Okay, this is 1 1 1 0, and add, you are adding this, right, m. So 0 1 0 1, so if you add, you get this number, right. So this is q remains same, this is q minus 1, and then again we are going to shift it right. So now you are shifting, you are going to put another 0 here, right, you are going to put another 0 here, so this becomes 1 1 1, this 1 from here has come here, 1 1 0 0. So if you see, the final answer will be in a and q, right. This is the answer which we get. This is equivalent to 30 if you see. Okay, 2 4 8 and 16. Okay, so that comes to 30. So this is the answer which we get. Is this algorithm clear to all of you now? Can anybody has got any doubt? Tell me. Can somebody say yes or no, so that we know? Okay, so you can expect these kind of questions for your comprehensive also, right? So essentially, in the last shift, y is 0 is shifted. Okay, here, right? Because this last is 0, right? So it will whatever is the last bit, that comes in from here. It is known as arithmetic shift. Okay, in this it is 1 here. Here it is 1 here. So when you push it, whatever was the last MSB, that comes in here. Is it okay, Shriya? Okay. Okay. So, no, the entire data is shifted to the right, right? So in the MSB there will be an empty. So whatever was there in the MSB, that will be put into that register. That is known as arithmetic shift. The entire data has been shifted here. If you see, this one has come here, so this has become 3 ones here. This 0 has come here. The entire a q minus 1 will be shifted. It will show since it's a 4-bit data, after 4 cycles of operation it will stop. Okay, so now let us revisit this. Okay, what we have done is, okay, if we are multiplying two numbers, okay, just whenever there is an like what is this actually? Okay, whenever there are a 1 is there, right? If you see this number, okay, what is this? 2 to the power of 4 minus 2 to the power of 1. So actually you are taking one more q to the power of n minus 1 here. So if you see this 1 means it's a starting of a 1. Whenever there is a starting of a 1, okay, we add that number here. And then whenever there is 1 to 1, we don't do anything. 1 to 1, we don't do anything. From 1 to 0, we subtract, right? So when you are going from 1 to 0. So it is only, see, if you see from here, what we have represented this number like this. Okay, what is this representation? This representation is nothing but whenever there is a 0 to 1, you add, and 1 to 0 you subtract, and 1 to 1 you don't do anything, and 1 to 0 to 0 also you don't do anything. Like in this case also, there are like here 1 to 1. So in a 1 has started, like 0 to 1 it has started, you have put 2 to the power of 6, again 1, okay, 1 to 1 we don't do anything, then again 1 to 0 we have put a negative sign, 0 to 0 we have not put anything, 0 to 1 again we have put a positive, and 1 to 1 we have not done anything, 1 to 0 we have put a negative. Okay, so if you understand this expression, then the Booth algorithm does the same thing. Whatever is written here, it's done in 4 steps, right? Like this, the Booth algorithm does the same thing. Okay, whatever this expression, it is trying to implement this expression from here, right? It is So if you see these transitions, if you try to understand, okay. So this is an Booth's algorithm. So this is how the circuit is implemented. So if you see the chart once again, so we are okay initializing a to 0, okay, q minus 1 to 0, m is a multiplicand, q is a multiplier, count is n, right. So here so if you write an m and then n minus m, right. So this is how it goes on, right. So this is the algorithm, okay. This is the hardware implementation. You have an a register, you have a q register, this is q minus 1 register, there will be a counter, add, subtraction, this also we have learnt in our theory classes, add, subtractor, this is m, and this is a controller, okay. So whereas this, let me do this correction here itself so that you don't have a problem. Okay, I did it in an Excel sheet and pasted here, so I'll change that. Okay, this is m, okay. So you are doing an a minus m or a plus m. So this is going to be m and this is going to be minus m, okay, remember. So let me take on with the negative number also and see what happens, okay. So I am writing minus 3 into 4, okay. Try to understand how this table is also, so that it will become pretty clear to you. You will not do any mistakes in the exam, okay. Now this is 3, right, 0 0 1 1, okay. This is m minus m, this is m. So I made an error here, so don't take care of that. In the PDF I will do the amendment. So this is m is 3, so minus 3 will be 1 1 0 1. So this is now minus 3 and this is 4 into, you are multiplying 3 into 4. So initially in the accumulator you have put 0 0 0, in q you have put 4, q n minus 1 is 0 and n. Now if I see, it is 0 and 0. So during the first clock cycle it will do nothing because it is 0 0. So the accumulator value will not change, you know. So a will remain a here in this case. A is going to remain a. Q is going to remain q. Q minus 1 is going to remain q minus 1, okay. Then again it is 0 0 0, right. And now after having done that, okay, in the negative edge of the clock, like I explained in the last class, this is going to shift right, okay. Shift right means the MSB will again be repeated here. So 0 0 0 here, so this 0 has come here, this has pushed 0 1 0 here, now this 0 has come here, again it is 0 0. So we don't do anything in the next positive edge of the clock also, nothing is going to happen. So accumulator is going to remain again 0 here, q is going to remain as such, q minus 1 as such, okay. And then again you are going to shift it right. So again 1 0 has come here, so this has become 1 here, it is 0 here. Now in the third clock it is 1 0, okay. 1 0 means it has to subtract. Subtract means a minus m, this is m, this is minus m, right, minus, it is written minus. So 0 0 1 0, so this will become 0 0 1 1, we have subtracted it, okay. This is going to remain same, this is going to remain same, again it is going to shift right. So 0 0 0 1, so this 1 has come here, 0 0, this 1 has gone out here, right. So again it is 0 1 here, 0 1 here means in the last clock it has to add. So this is the data which was available here, and I am going to add this, right, 1 1 0 1 and this. If you are going to add both of them, you are going to get 1 1 0 this. Again I am going to shift it right. So now if you see shift right means I am getting it 1 here. So this is going to be 1. I am going to shift, I am going to put a 1 here, right. So I get this answer. Now what is this? This entire thing is minus 12, right. It's a complement of 12. If you try to take a complement of 12, you will get this answer. So this Booth's algorithm is good enough. It works fine even for 2's multiplication also. Is it okay? Has anybody has got any doubt? Yeah, Vijay, what is the doubt? Sir, what if starting from 0 we put a negative sign? I didn't get your question. Okay.
So in that slide number 4 where you were showing those signs,
Slide number,
just
yeah, yeah.
before this one, sir. Just before this.
Yeah,
Yes, sir. Over here, you told that if it's starting from 1, we took a positive sign
yeah.
for that 2 power. So what if it's starting from 0? Will we take a negative sign there?
Uh, no, no. If it is making a 0 to 1 transition, right, we start from the 1 here. Okay, the algorithm is, this is just an illustration ki, okay, if you have ones from here, right, then it will be positive. 1 to 0 it will make a negative, 0 to 1 it will make a positive, again 1 to 0 it will make a negative. Okay, the Booth's algorithm basically, you split the number into number of ones and number of zeros, and you only take care of the transitions from 0 to 1 and 1 to 0. Whenever there is a 1 to 1 or 0 to 0, you don't do anything. If it is a 0 to 1, you make a plus transition, and 1 to 0 you make an 0. Here we are assuming, okay, there will be a 0 here, so 0 to 1 we are making positive transition here, right. Similarly, in the end we are assuming there is a 0 here, so 1 to 0 we are making a negative transition, right.
All right, sir.
Oh,
Understood that, sir.
okay. Now, who else do we use, because we can't multiply negative? Yeah, in sequence we use a Booth algorithm because no, this takes care of both, and it is faster also. It takes two bits, and it's not faster, but it basically, yeah, you can say, because it can handle both positive and negative number. Okay, there are some slightly better modified Booth's algorithm and all, so it will become very complex, so we leave it at that. So now you know how to do a multiplication, addition of all binary numbers. So this is the algorithm, and this is the hardware. So this hardware also is, I think, it's nothing. We have all learnt about counters, registers, subtractors. So these things, we have done that. So this is how a microprocessor would do the algorithm, calculation at the way. Even for a matter in your calculator also, some algorithm will run like this. Finally, the program has to run, whatever you give the commands has to run in some hardware ultimately. So this will be the hardware, and this will be the program. So the once you do initiate then multiplication command, you can understand in the background, okay, all these things will happen sequentially, first step, second step, third step. So those many clock cycles. So if the clock is in 1 gigahertz, or even if it is say in 1 megahertz, for a calculator, even if it's in kilohertz, so all these steps will happen one by one, one by one, one by one. So by the time it does 4 clocks, right, it will be 4 microseconds, even if it is 1 megahertz signal, 4 microseconds. So you can't even you can't a human being cannot distinguish the data. So it will appear as if the moment you have pressed equal to, the answer has come. But remember, in the background all these things will happen, and it will get implemented in some hardware like this. Okay, so is that okay for all of you? So you might have some questions. So I'm not sure, I might give some subjective questions also this time, and I'm just waiting for AJSRD to explain what is the kind of platform which they are going to offer. You also might have received a mail, right? So based on that, we'll decide on the mode of examination. Okay, so that's all for today.